So in yesterday's lecture, I tried to explain the theme of the 3 lectures, and I talked at length about what is called the new intersection theorem in commutative algebra. And towards the end, I talked about a new perspective on that result and stated a strengthening of the new intersection theorem, at least for rings containing fields. So my goal today is to give you a complete proof of that result, well, complete modulo a few details. And it's based on what's called the class inequality for differential modules. So today's lecture is going to be extracted mostly from these 2 papers. This has already appeared. So it's joint work with Avramo, Buchweitz, myself. And the second work, which is ongoing, is joint also with Christensen, Lars Christensen, and Greg Piepmeier. Okay, so in some sense, today's lecture, this material begins anew. In fact, it begins at the very beginning of homological algebra in the following sense. So as yesterday, R will be, soon it will be a commutative Noetherian ring. For the moment, it's just some ring. So as I said, you could imagine that you're working over polynomial rings or quotients of polynomial rings, if you wish. So a differential R module, so here's a definition. The basic definition is that a differential module is a pair where D is an R module and delta is an R linear map so it's an endomorphism of D and the crucial property is that the square of this is 0. So a differential module is nothing but a square 0 endomorphism of a module. Yeah? So it's a module with a square 0 endomorphism. So it's a very primitive structure, and as I'll soon explain, this is the structure that underlies complexes, differential modules over differential graded algebras, etc. It's somehow it's a very primitive structure underlying a lot of structures in homological algebra. Now, because of this condition, obviously the image of delta contains the kernel of delta. So image of delta is contained in the kernel of delta. And as for complexes, you can talk of the homology of the differential module. So it's just this. So this is the homology of T. Yeah? Notice that in this case there's no grading unlike complexes. It's just a module over R. And so when I talk of differential modules, I should be talking of pairs, but I'll just talk of D as a differential module with the understanding that there is a square 0 endomorphism delta. And you can expect what the notion of a morphism is. So a morphism is a map of pairs. If I want to emphasize which module the delta depends on, I'll put D here. Is a map, so I mean an R linear map from D to E. And of course, you want it to commute with the differential. So it's the natural definition. So it's just a map of R modules which commutes with the differential structure on the modules, right? And such a map again induces a map on homology and as usual I'll call F quasi-isomorphism if this is an isomorphism. Quasi-isomorphism. is bijective. And I might write to indicate that there's f is a quasi-isomorphism from D to E. Now, you can look at the category of differential modules and their morphisms. So I won't dwell too much on these categorical aspects, but just let me put this down. So delta R is the category of differential modules, R modules, and their morphisms. And it's an elementary observation that this is an abelian category. So you can either check this directly, or maybe the better way to do it is to just make the observation that a differential module is nothing but a module over the dual numbers. Delta R is just the module category, the modules over the ring of dual numbers. So this is Rx over R epsilon over epsilon square. Yeah. The differential on the module gives you an action of R epsilon on D. So you can identify differential modules as module over R epsilon, and then it's clear that it's a abelian category. Okay. Now, let me give you examples to maybe it's, let me start afresh. So in this lecture, I want to discuss two examples of differential. I mean, there are in fact two main sources for differential modules. One is complexes over rings, and the other one is DG modules over DG algebra, graded algebras. So the first one, the first example is that if you take any complex so you take any complex of R module, so this is a complex you can construct a differential module from it, which I'll denote C plus. So this is the differential module. So the underlying module is the obvious one. You have to take the sum of these. And so over all I. And I have to tell you what the differential on this module is. And it's, you could just take the sum of the differentials. Yeah? And the property that the composite of consecutive differential is 0 tells you that this is a differential on the module. And note that in this case, the homology of this differential module is nothing but the direct sum of the homologies of the complex. So every complex gives rise to a differential module.